Hmm. Hello, everyone. Great. All right, welcome to class today. So we're currently on week 12, right? So today we have our exam during the second half of class. Pretty good exam, I think. We made a good one. Should be fun, I think. Um, so yeah, um, we'll have the exam during the second half. During the first half, we'll just do a short lecture. I'll introduce CNNs basically kind of as a topic. I believe we will start doing our mini project presentations a week from today, right? You guys are working on your data scraping and creating a VET GPT. All you have to do is get some information from the web related to VET things, text, and instead of the Huck Finn file, you just use that and train it on the GPU. That's it, right? So it shouldn't be that difficult. If you're having a lot of difficulty, you're looking at this the wrong way. Okay. And use any tools that you can find. There's many tools for web scraping. Actually, the purpose of the project is more on the web scraping side. That should be the challenge, not the GPT. Okay. Does that make sense? Are there any questions about that? Yes, sir. Please.
How many how many articles are you expecting? Are you just expecting like one or two?
Again, at the end of the day, it's kind of your choice in a sense, right?
Yeah.
Because it's a competition, right? How do we measure it qualitatively, honestly? But you kind of want to win. What do you do?
Multiple.
Yeah.
Yeah.
You see what I'm saying? So I just want you guys to understand that process, basically. Yes, sir.
It's the same as last exam. We're allowed one page at work.
Yes, most definitely. Any other questions? Yeah.
The data, like we are getting most of the header and footer files like repeatedly.
Yeah, like the HTML things.
Yeah,
Yeah, scrape it out. Yeah, I mean, you really just need the text, right? You really just want the text. I mean, that's part of the whole idea of, machine learning. The hard part is getting the data. Like, if anything, you'll just use the GPT I gave you. You'll just use you'll have like 30 algorithms in your toolbox, but the data is hard. Getting it in the format is hard. See that? So yeah, clean it as best as you can. And as I said, the goal is to win, to produce the best at GPT that you can. Make sense? Any other questions, guys? All right, great. We'll probably have one more mini project, right? Or term project, I should say, and it's going to be related to stable diffusion. So that's kind of the last algorithm that we're going to discuss. This one is the last of the big ones, right? So the big ones are the GPTs or the stable diffusions, right? So what are the stable diffusions? You write, I want myself as a cowboy on the moon, right? And it generates that, right? So obviously, I'll show you guys just briefly how you can do that, but that's more transfer learning, so it would be something I would cover in 5:30. But I'll just show you like what you can do with those tools. The code I'll give you from scratch will not have that capability. Okay. But it will be a stable diffusion light type of an algorithm. And basically what I would like you to do is kind of like a conditional generation of images of some kind. So I'll do an example and then you'll have that. And that one can be your term project. So you can do that in groups of 3. Does that make sense? So that will be the final term project. Basically, given that we are running out of time, right? If you think about it for week 12, then we got Thanksgiving coming up and everything. So you do need to come to class, though, I remind you. Right? So I'll be taking attendance from now on. All right. Any questions? And, I should say stable diffusion is about images, right? So it's about generating images, generative AI of images. So I will start with images now. So we've covered text processing with the GPTs. I'm throwing in basic things about machine learning like we did last week where we cover optimization, the chain rule derivatives. We talked about the vector space model, all those ideas. I may talk about a couple more of the traditional algorithms here and there, and then Stable diffusion is the next topic. Okay, so today I'll just do a quick introduction just of CNNs and what they are, right? And just keep in mind, when we look at stable diffusion, for instance, it'll have things, a lot of the concepts like maybe a convolutional layer, right? Which is what CNNs are, but it'll also have embeddings. It'll also have some text ideas or conditional information going in. So got it? All right. So this is kind of just the first of this discussion of the basic algorithms. All right. So I'll just start with some code. So we'll start running CNN. So I will start my Anaconda prompt. So it's a huge area, right? It's actually the area that first made deep learning famous, images, right? And so it's definitely, there's a lot there. So, right. So it's 2024. Learning ideas. So that's what we've covered so far. So I'm going to create a new folder and I'm just going to put it under CNNs, convolutions. So I'll just give some of the basics today and then we will get into some of these ideas in more depth. But I will do an analogy of what a CNN kind of does. Okay. So that should give you the intuition. Okay. So our environment should be ML 2024, I believe. Uh, 38. All right, so I'll start the Jupyter notebook, and then I'll just start discussing the lecture. Basically, all the code is already available on the GitHub, so I'll show you where a lot of these things are, okay, that we will be covering. Okay. Okay. All right, so here we are. Create a new Jupyter. And let's just call it our first CNN. Okay. All right. So the code for this that I'll be using is already on the GitHub. So in the usual place, you can take a look under deep learning, second edition, chapter 6, right? And we'll be looking at this one today, MNIST CNNs. There's several CNNs here that we might discuss, but we'll start with this basic one. We'll also kind of go over this as this has the intuition, basically, of what a convolution is. And that's really, I think, the key thing for you to understand is, what is this convolution idea? All right, so we'll go over this. We'll start with MNIST CNNs. At the end of this sequence, although I will be throwing in, several other topics here and there, of traditional machine learning, at the end of this sequence, my plan is to go to the repo, this algorithm, which will, if you want to start looking at it already, you can for your term project, latent diffusion. So we're going to look at what diffusion models are, right? And basically they're an algorithm of generative AI, the state of the art right now, very interesting ideas of how images are generated, right? So CNNs traditionally have been for classification initially, but they have a lot of power in basically you can think of them as feature extractor. Okay, so that's a key intuition. And then we're going to look at, ultimately finish up with something like stable diffusion. So what can stable diffusion do, right? So, this stable diffusion model here, you'll train from scratch for your term project, right? But generally speaking, these stable diffusion models are actually have to be pre-trained, by large groups because they require massive amounts of computing data and all that. So it's similar idea to a GPT, right? So you've learned that a GPT requires a lot of pre-training, right? And then the fine-tuning, right? So, that idea of fine-tuning is something that I don't cover in this class. It's covered in the ITS 530 class, the next class, right? So in this project, you will just do things from scratch, but the state of the art is that you take those models, pre-train them on massive amounts of data, and then you fine-tune them for a specific task. So for instance, I have a funny example here of what you can do with them. So where is it? So, yeah. Okay. So you can see these are examples of these models. As you can see, this is me. I took myself and made myself into very awesome pictures. And this is the power of things that you can do, right? So that's me by Gen AI. I asked to look like a professor in the 1940s, and that's what it did. I then was told by many people to get that outfit because I would look really good. So, in any case, so this is a tool called Replicate. You can do really amazing things with it, but it's all the stable diffusion models with the difference that these are pre-trained models that you fine tune. So I'll show you another example. This one, I made myself as Wolverine. Right? So look good. Actually, these things make you more handsome than you really are, or better looking. So I was really impressed by that. And I think I have one more. A second. Yeah, see, this one is an owl playing with it. Just trying to this one didn't come out well, but it was a mouse on a dragon. And this is actually stable diffusion, if I remember correctly. So there are more powerful models than this one. Flux is a more powerful one. This was a cat in the military. And I made myself into a samurai, which, I really like this. And I made myself into a Viking invading England, right? So you can do this yourself with the, I mean, I'm not kidding. This is generative AI. And I made myself into a cowboy. All right, so you can do all these things. These are amazing things that you can do, right? But they require fine-tuning pre-trained models. We're not there yet. And as I said, these are the kinds of things that I do cover in 530, which is the next class. All right. In this one, we will just start at the beginning with a from scratch training of a model, and then, we'll generate numbers probably. And let's see in your term project what you can do with it. Okay. Does that make sense, guys? All right. So these ideas, as you can see, they're about generating images. So obviously, part of it is the convolutional neural networks, right? That are feature extractors, and they help you to process images more efficiently, right? So this is pretty advanced. Now let's go to kind of the other end and the starting point, okay? So I'm going to go ahead and go back to my repo. I go back to my repo here. Yeah, so deep learning algorithms, which is, the course. As usual, the materials are also there if you want to, you should start reading. So if you go to the course website that I have, and I'll add this to Brightspace also. Give me a sec. I'll add this to Brightspace, but the material that you should follow along with your reading is here. You can start reading chapter 6, convolutional neural networks, and this will have basically a lot of the background that you can start following along, as I usually do, like a block type of a thing. And I describe the code here, which is kind of the code that I will be describing starting today. So I don't know if we'll finish today, but we'll see. All right, so now that that's kind of addressed, so let's go back to the repo, GitHub. All right, and I'm gonna go to deep learning algorithms, second edition, chapter 6. All right, so ultimately, without getting, making things too complicated, right, and giving you all these, formulas and everything like that, what is a convolution, right? What is a convolution? And this is actually very interesting because a convolution is kind of this process. It's a transformation of an image into another image via a filter. Okay, that's kind of the way that you can think about it. So, many years ago, when I was studying this, we actually, would spend a whole course just learning all these filters. Do you see what I'm saying? So you would learn all these filters that you would apply to images, and that would basically transform the images from one thing to another thing. But this is 15 years ago, right? So like half of you would have been employed in just creating these filters. And you would have taken maybe in your whole career, you'd create one or two filters, right? That were very useful. This is how it was done. As it turns out, what happened later on with CNNs is that they discovered a method where the neural nets could figure out these filters. And it just became a much better approach, right? So we went from extracting features kind of manually to extracting features automatically. So let me give you an example. So here I have, for instance, this example, right? It's code. You can run this if you'd like, just to see how it works. But I have this image. Do you guys see that? I have this image, and I'm going to create a filter that might be 5 by 5 or something like that, right? And I have to put in the numbers, the specific numbers in that filter. And then I have to run that filter through the image. And what's going to happen is that logic that I implement in the filter will change the image into a new image. You see that? And so here you can see I have this original image. I run through it what is called a horizontal edge filter, such as this one. And if you look carefully, look at it carefully, right? It's got edges. And you will see that now you kind of have these highlighted, this is darker than the rest. Do you guys see that? And so you can think of it as this filter created a new representation of the image where it highlights just specific things about it. Like for instance, the vertical edge, right? Or sorry, the horizontal edge. Why is that important? It might be important because you're trying to detect something, right? You're trying to build a model that would take that image and tell you, yeah, that's a cup of coffee. And the way that I find it is by finding these edges. Does that make sense? So, but the problem was that this had to be created manually. I'm not kidding about this. This is how it used to be even like 15 years ago. So machine learning did displace a lot of people and took their jobs, 15 years ago, because a lot of these people that worked on creating these filters basically became obsolete. Okay. And that's because of CNNs. Because what the trick is, if you think about it, you start with an image, which it's a tensor. So it's a grid, right? And then you're going to perform an operation on it with this little filter that is 3 by 3. And the output will be something like that. All right. And then I can have another example here where I do a vertical edge detector on the same image. And now you can see that everything is kind of lighter scale except for this one. This is darker. So you can see an edge has been found here that is vertical. Does that make sense? So this used to be the process of, processing images. You would basically take an image, convert it into something like this, and then this is what you would feed into your KNN or support vector machines or whatever it is, and and then you would train the model to detect if it's a cup or a cat or whatever. Okay, grass maybe. All right, so that used to be the process, but the problem was, as I said, that this had to be created by humans. So initially, you can create the first 20 filters probably very easily, right? Get a couple of very smart people, they boom, 20 filters. But after that, creating the 21st, the 22nd takes a lot of effort. It's really hard, right? And so somebody decided, okay, somebody tried this technique called, convolutional neural networks, right? And what they do is something similar. They treat basically the filter as the weights matrix, if you want to think of it that way, right? So what does that mean? You can start with a filter that just has random values. Do you see that? And then you give it the image and you kind of multiply it times this filter, and then it'll output, a processed image, right? But depending on your task, the model will learn what the weight should be that will benefit, that will improve your performance. Do you see that? So it's almost, you can think of it this way, right? So you have some model, it gets an image, and you're trying to detect if it's a cat or a dog, right? So you take the image, you kind of run this filter on the image. Initially, the values are random and it predicts, and it does very poorly, right? But it's going to use that information during back propagation to do what? To update the weights of the filter. And eventually, what can happen is that the performance is going to start to improve. You've learned weights for a filter, and now these filters don't just have to be vertical edge filters or horizontal edge filters. They can be anything that is helpful for the model to do the task. Do you see that? So now these things can be used for many, 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 many things. Got it? Does that make sense, guys? Any questions on that idea? So that is, in a nutshell, the intuition of convolutions, okay, and how convolutional neural networks work. Now imagine that we live in a world where we have massive amounts of data, right? So they'll take millions of images, run them through a CNN that trains this filter. And by the way, you don't just use one filter anymore, but you'll have 36 filters or 64 filters on every layer, right? And then you're learning all those weights for all these filters. So now what you end up with is an architecture that can take an image and produce hundreds, if not thousands of versions of that image highlighting different things that can be used together for some specific task. Does that make sense? So now think of it as, okay, I want to have a vertical edge detector, a horizontal edge detector. I also want a detector of eyes. I also want a detector of fur. I also want a detector of whatever, right? And all of these filters, you don't have to really you just set up that they should be 3x3, but you don't really have to put in the values in there. Instead, because the model is training on millions, right, of images, it's going to learn it by itself because at the end of the day, it starts to detect little edges that become circles, that become more complex figures, and so on. Any questions, guys, about that idea? So we'll come back to it and definitely read the material that I provided, but that's the intuition basically of how CNNs work. Okay, so an image, that's the power of it, right? So a lot of people nowadays use these models just to extract features automatically, right? That's why the problem of images has become so easy to kind of to tackle, because you can take a pre-trained model that has all these filters that it already learned how to produce. And so then you can run any image on it and you can expect that the output of it is going to be a representation of the image that gives you a lot of information. Like there might be one of the filters that says, okay, those are faces. You know, you guys have seen, you know, nowadays your phone can detect faces easily and things like that. And it's because, you know, they might have these types of filter. Okay. Got it? All right. So they're feature extractors basically, and they are done automatically. So anyway, so this is the intuition of CNNs ultimately that you run a filter. So you have an input, you run a filter through it, and then you get an output, which is a representation of that image with additional information. Could be the skeleton of a person, could be, you know, a face of a person, hair, whatever it is, right? Whatever you need for your problem, it might detect for you, and it does it automatically. And the assumption, of course, is that there would be a lot of data available. Okay. All right. So anyway, so that's kind of the intuition of a CNN, like the math intuition. Now we can go back and just do a simple example of a CNN. We'll start there today, and then you know build up from that idea. So let me get all right, so obviously we're gonna need some data. So I usually don't like you know downloading a whole bunch of data. So we're just gonna use Torch Vision for this one and download some MNIST. You know, we'll start with MNIST, which is where we should start, but you know we'll build up from here. And like I said, my goal is really to cover something like stable latent diffusion. All right, so this let's go to the repo. Okay, so I'm gonna go to Chapter 6, as I said. I'm going to look at MNIST CNN. Okay. So I have here, you know, this is the code that we're going to go over. We're going to use import Torch Vision. We can install it if we don't have it available. And this will just give us the MNIST data set. From there, we'll create a data loader, right? We'll start to think about how to create a very simple CNN architecture, right? And you know, kind of what that entails, and keeping in mind the intuition of what it is, and then basically train our model, look at the performance of it, and then you know, and then measure performance. Basically, and if time permits today, or if not next week, we'll go over some with random data, some playing with convolutions and kind of what they do and everything like that. All right. So let's go ahead and get started. So, you know, this is MNIST CNN. MNIST, if you don't know, is a data set of image, handwritten digits. It's been I think it was created by Jean LeCun. It's been around for a long time. Okay. So let's go ahead and copy those libraries. Oops, sorry. First, all right, so basically the same libraries as before: Torch, NumPy, Torch Vision, from which we will use data sets, some transforms that we can perform, matplotlib, and pill in this case for image viewing, right? So we're going to be looking at images, which is, you know, doesn't get more traditional than images in machine learning, right? Okay, so I probably have this already installed, I assume. Oh, no, I don't. So let's install Torch Vision. Okay. That's taking a while there. So again, what is an image at the end of the day? An image is just a tensor, right? So it's going to have, it's a grid, two-dimensional array. These are, by the way, black and white images. I'll start with these. Later on, we'll have color. That might, so that changes a little bit the architecture that we will be using. Okay. So I guess hopefully it'll work. So let me move on to a few more. I'll copy these libraries. And I will copy these. It's taking a lot. Okay. All right, well, it's doing that. So I guess I'll go over the code. Not sure why it's taking so long. Some of the other libraries are sklearn metrics. This is a classification problem, right? So we're just going to classify images. So precision, recall, F measure, you should know these already and be familiar with them. We'll use also NN and Optim. And we'll take the same approach as before, just creating the classes, etc. Parameters are the learning rate, number of epochs, 20 or so, and the batch size, the number of images that we're going to feed to our model. Okay. All right, so then we instead of loading the data from a data set, which is perfectly fine and something that we will need to know about, we can just use data sets, right, from Torch Vision to load in our images. Okay, so I'm going to go ahead and grab that. I'm not sure why it's taking so long. It's running, right? Anyway, let's go over the code. Okay, so basically we'll create a data path where the data will be downloaded. We'll invoke something called datasets. This datasets comes from Torch Vision here. So from Torch Vision, import datasets. Okay, and we're going to specify this path, which is where the data should be saved. And then we're just going to specify if we want the train set or the test set and to download it. All right, and that should be in MNIST train. Okay. This is going to be the MNIST test. Okay, MNIST test. So the same idea. We just say train false, so it downloads the test set. Sure. Huh? Is the Wi-Fi slow? You think that's what it is? Yeah. Sure is taking its time. All right, so let's, I guess, go over the code for now. And all right, so then after that, we can use the GitHub here where I have it. So basically, we're going to create from data sets. We're going to take this approach. We're, so let's see. We got MNIST train, MNIST test. They get downloaded. And then datasets.mnist will grab from data path, the data that was downloaded here. We specify if we want the train or the test. And we can apply these transforms basically. So this datasets MNIST has this approach that allows you to apply several transforms to the things that you're downloading. Okay, so this is something that will get some time to, to get used to, but basically, think of it as you download the whole data set and then you apply these transforms to it. So in this case, this transform here just basically converts everything to a tensor without you having to do anything else. You just almost kind of specify that you want to convert these to torch tensors. So this then would basically give me MNIST train TR and MNIST test TR. All right, so at this point, basically I display an image, but I think this thing is still not working.
Restart.
Huh?
Restart.
Restart it? Okay. Do that. Okay. Oh, nice. Thank you. All right. Appreciate that. So hopefully we have this working now. All right. So all right. Let's give it a minute. Okay, so it completed. Good. All right, so we've got the libraries now. All right, so we're going to proceed with the parameters. Now we can download the data. Okay, there it is, downloading. Jean LeCun. Okay, as you can see, it takes a little bit, but this data set is not as big compared to other data sets, right? So that can be much, much larger. Okay. So it's downloading a lot of data sets there. Hopefully it only does this once though, so shouldn't be such an issue. All right, so I assume it finished. So I'm going to run it again. You can see now it's basically downloaded. Let's do the other one. Okay, no issues it seems. So all the data has now been downloaded. All right, and we want to, so this is, if you want to start building a CNN or something like that with images, this is probably the quickest way to start. Obviously, at some point, you do need to be able to read your data from like a folder, right, where you have actual images and all that. And you can use things like Torch Vision for that. All right, so I think everything worked unless you see a problem. So let's go ahead and run these transforms now, right? So I've done MNIST train and test. Guys, all right, so let's run MNIST train. Guys, right there. All right. So let's look at this one. So as I said, now that we've downloaded the data, we can select a train set, we don't download it, and we have this mechanism, if you look, transform equal, right? So it's a kind of a thing, a parameter that you can set, and you can provide to it the construct transforms. So the construct transforms comes from here, from Torch Vision, and it's just a really efficient and quick way to do lots of things to all your images. You can convert them to tensors. You can normalize them. You can, do lots of things through here. And you can actually do a pipeline. So what I mean by that is, hey, let's make it a tensor, normalize it, and do these other things. And you can use a mechanism called a compose, the transform compose for that. All right, so we can take a look at that. So actually, that's what this is using, right? So transforms equal transforms dot compose. So then basically here you can provide all the transformations that you want, and they will be applied in a pipeline type of a way. And that can be very, make your life very easy, right? Does that make sense, guys? So you don't have to do all that manually. So that's kind of the idea here. All right. So in this case, I'm just going to convert things to torch tensors sort of easily. So let's go ahead and run it. So I think that ran successfully. Okay. Then I'm going to pursue the next one, which is going to be for the test set. So in this example, I'm just converting things to tensors so that they will work on the PyTorch computational graph, as you know. All right, so basically my data is set. So now we might want to look at the data, all right, and that's kind of what I'm going to do now. All right, so to display an image, I'm just going to go ahead and use PIL. So what is PIL? So you have here from PIL import images is basically like a Python image processing library, very useful that you can use. So here you can see I'm going to say I want from MNIST test TR, so that's this data set. I'm going to specify an index. Because it's a torch tensor, I'm going to convert it to a NumPy tensor, and then I'm going to feed it into image PIL, or an image from PIL, so that I can view the image. Make sense? Okay, so I'm going to go ahead and do that, and you can see that looks like a 6. So this is the data that we're using. It's the simplest and most classic example of when using images. The challenging part may be sometimes when we have to switch from black and white to color images, because color images will have more, think of a black and white image as just a grid that it might be 32 by 32, but a color image will be a cube. So it's no longer just like a flat array. It's going to be, a two-dimensional array is going to be a three-dimensional array. So we have to deal with the 3 dimensions, okay, for the different colors. But in this case, we're just talking about black and white. So let's try another one just for to test things. So there should be in tests, I think there's a 4,000. And it's, what is that, like a 9 and so on, right? So a lot of the examples that you do when you're processing simple images are going to be MNIST. If we do color, it'll be like Fashion MNIST or something like that, which I think has color images, or there's a few other ones that have color images. All right, so we've looked at the data set. Okay, obviously, as we start to process our tensors for our neural network, we want to print out the shape. So in this case, I'm going to do the MNIST train tr data.shape. And you can see that this says that it is 60,000 by 28 by 28. So what that means is that there are 60,000 images in there, right? And the images are 28 by 28. So once again, dimensions are really important, right? There are various ways of processing this, okay? And PyTorch actually has specific requirements as to how it wants the tensors, okay? So we're gonna take a look at the next one here. So we've done this train TR, okay? Test TR, actually, is the one I want. All right, so MNIST test TR, this one is the test set, and it has 10,000 at 28 by 28. So the images are the same dimensions, but there's only 10,000 images in the test set. All right, now let's go ahead and do the data loader. So Control copy. All right, so as you can see, we're going to use torch.utils.data.data loader. This is a tool that we've used before, right? And it's highly recommended that you use this one. The data, it's already in the format that we need here, okay? So we just have to feed it into the data loader, basically, okay? The batch size is going to be 32 for the training. For the test set, we don't have to train in batches. Therefore, you can just say 10,000 for all the samples. All right, and then shuffle is true. And if you remember, what does shuffle do? Every time, every epoch, right, that you feed the data into the neural net, the data is shuffled, basically, and it does that for you. All right, so this is train DL and test DL. Okay, no errors. That's good. So, we have our data processed in the format that we need. I have the convenient print metrics function that we have used before. This is the exact same thing we've used in the past. I'm just going to add that. All right, now there's a lot of ways of doing this, but we are ready to build our first CNN, all right? So just something very straightforward. So we will. All right, so let's just focus on the architecture right now. So I'm going to copy this one. And then we can discuss it. Oh, there we go. All right, so obviously this is like any other neural network that we've seen in the past in the sense that you can add multiple layers, right? You can make it deeper and deeper and deeper, except that the layers in a CNN now have more complexity, right? There's more involved. So I want to show first the things that are common and then the things that are a little bit different from how we have done things before, right? So we've been taking this approach of using object-oriented classes to create our models, right? Our architectures. You can see I'm doing the same thing here. Class classifier underscore CNN. It inherits nn.module, right? So you can see that there. We have two functions, the init function, and then we have the forward function. So that's exactly the same thing that we've been doing before. Notice that the forward function is actually really straightforward. All you do is you receive the inputs, and then it returns self.model. You see that? And it gives the inputs to it. So it's very easy. But then you have to ask the question, what is self.model? So if you look in the init function, we have the definition of self.model, okay? First, we do super init, which we've discussed before, just the instantiation of the inherited class. And then after that, we do this one. Now, if you notice in the past, we have done x goes into the function, produces another x, which becomes the input x of the next function, and so on, right? We've been doing this. And I think last week or so, I showed you this. There was a part in the GPT where we used this. Do you guys remember? Do you remember where we used this in the GPT? To create the blocks, right? I think you guys remember there's a section in the GPT. So I've shown you this before, and I'll show you again. So if we go to the GPT code, deep learning algorithms, second edition, chapter 10, transformers, GPTs, the Huck Finn code. There's a section in here where I use that approach of NN sequential. And it should be there it is. Do you see that? NN.sequential. And then basically we provide a pointer really to a list comprehension where we iterate for index in number of layers, we instantiate what? Blocks. So this is the part where we created block followed by a block, followed by a block, followed by a block. Because when in NN sequential, you can create architecture kind of line by line, and then the data will go through it, right? So we did this before, you saw it here, and now we're seeing it in the CNN, which is usually where I traditionally like to use NN sequential because there's so much code going on. So it just makes your life easier. So basically here, this is one of the two main approaches that I have used for creating architectures in neural networks, right? So in this case, what we're going to do is notice that there is no X going in here, right? So there is no such thing as, there is not that, is what I'm trying to say, if you notice, right? And then an X coming out over here, which becomes the input to the next X. This is one of the approaches that we have used in the past, but not the one that NN sequential requires, right? So I can remove that from there. And instead, the way that this works is you create the architecture and you can assume that the X just goes through the whole thing. Got it? Yeah. All right. So basically that's kind of, the technique. And so here we're just going to think about the architecture of the convolution. So usually when you do convolutions, you have at least two things that you're going to use. This thing called a conv the convolution, in this case, a conv2D, and something called the max pool. Okay, so the convolution will do what? We'll do this intuition I gave you before of taking an image and running a filter through it, right? And then once you do that, you get another image that comes out. Does that make sense? So let's say that you give it one image and there's 16 filters, right? So what comes out? In a simple example, you give it 28 by 28 by 1, you run it through the CNN layer, which has 16 filters, and you get 28 by 28 by 16. So each one of the images, you have a filter that runs through it, and you get a transformation of it, which might be a new way of viewing the image. Do you guys see that? So if I take a picture of this classroom, I get one image that just highlights green, and it shows me the pixels where green is present. And I have another image, another version that comes out that highlights red, and so on. Make sense? So that's basically what's happening there. So you have then the convolution, and then you have this idea of the max pool. And the max pool is an interesting thing. The idea is that you take the image that is 28 by 28 and you do what? You cut it in half. So if the image was 28 by 28, now it would be 14 by 14. So you're forcing the model to make the images smaller. And in a sense, it's like saying that you're forcing the model to be efficient, right? Stop, just be really efficient. Transform the image, but also make it smaller and smaller and smaller. Okay, because otherwise, think of this as you're taking one original image. Now you're making 16 or 32 versions of it. In the next layer, you take those 32 and you make more versions of it. So it could become very big, right? A lot of memory and everything. So there is this component of also narrowing things down, basically. All right. So in this case, then, the things that you have to specify here. So I have one convolutional layer, which is this one, then a second convolutional layer, and then you have a feed-forward layer, basically, which is your normal neural network layer. So what's important here to think about is that you're going to have one input, so you have a 28 by 28 by 1, right? And then you have 16 filters. You specify the size, so a filter of 5 by 5, how it moves on the image, and if it applies padding, basically. Okay? Does that make sense? So it processes the image, and it's going to give you a transformed version of the image that comes out. You can apply ReLU activations to it, which is the same thing as the other activations that we've talked about. And then you apply this max pool operation so that the images get cut, right? So maybe cut in half or whatever it is, right? So image that was 20 by 28 now should be 14 by 14. How the neural network does that, it's up to it because it's learning those ways, right? But it needs to make that transformation. Got it? Make sense? That's what a CNN is in essence. So then what happens in the second convolutional layer? You took out 16 versions of it. So now the input is 16 versions to it, right? And you're going to apply basically 32 filters to that, okay? With kernels of size 5, stride and everything. You apply the ReLU activation again, and you once again max pool it to make it smaller. Do you guys see that? And then finally, imagine that you have some kind of a tensor of some shape, right? Some kind of a tensor of some shape, and you do a flattening operation. What does that mean? It means that you make it into a single one-dimensional vector, so it becomes the normal type of layer that goes into, the neural networks that we've done before, right? So maybe now this flatten operation will figure out its own dimension, right? And if you notice here, what I did is I know what that dimension is. So I just plug it in here as 800. So ultimately what this is doing is the images go in, all these operations happen, and after the flatten operation, the vector would be of size 800. Does that make sense? Now there's obviously a way that I have to be able to figure out this dimension, and I'll show you in a little bit how we can calculate it. Okay, so something that you can calculate. After that, this flattened layer of 800 just gets, this is a normal feed forward. So this is just gets mapped from 800 to 512. You apply ReLU, then another linear layer from 512 to 10. Why 10? Because there are 10 classes for this problem. So you have images, you have 10 digits, right? 10 handwritten digits. You put in a 7 or an 8, and it should predict that it's a 7 or an 8. So there are 10 classes. And then you should, if you remember what was softmax, basically the softmax was making sure that the 10 probabilities add up to 1, right? And creating this idea of a distribution. So that's pretty much how you go about creating very simple CNNs, right? So you can have these you define a convolutional layer, which is usually made up of at least a convolution and the max pool. Then you can have a second convolutional layer made of a convolution and a max pool. And then finally, after that, it's just a regular neural network as we have defined them before. There is several versions of how to do this, of course. I'm just doing like a very simple one that applies to MNIST in our case. And at the end, you will receive an image and predict a class, basically. Does that make sense, guys? All right, so let's try it out. And you'll see other examples of this as we move in the semester. Keep in mind, you might think, oh, this looks very complicated and everything, right? There are pre-trained CNNs that have actual names like VGG, ResNet. I believe we will use something called UNet in the latent diffusion model. These are very deep networks that perform these tasks like 100 times. Okay, there's 100 layers or so, and so they're very, very, very deep. Okay, so anyway, so hopefully that makes sense. So today I'm showing you this approach of NN sequential. You've seen that in the GPT. I've shown you how to create a couple of convolutional layers to process images, and I've given you the intuition of what a convolution basically is. A filter applied to an image that produces another image. But in the context of CNNs, we humans don't need to provide the weights of the filter. Instead, the network learns them for us. And that's, a game changer. All right, so I'm going to run it. All right, so the model should be there. Sorry. Yeah, here. So now what are we going to do? This should be the exact same thing that we've done before, our train function. Let's go over here. I'm going to close this because I don't. All right, so I have my training function just like before. If you notice, a lot of these things are starting to become very familiar, right? So I'm not changing many things. Same approach, an epochs model, loss function, optim. This is a classification problem, so it's going to use a loss function called cross entropy, which is definitely one of the things that I still need to cover. But as you can see, basically for epoch and n epochs, right? And every epoch, we are going to grab train DL, which is our data loader, and we're going to grab XB and YB, XB being the batch of images and YB being the corresponding batch of labels. Excuse me. So here then, the model gets XB, the batch of images, and it does what? It predicts what those are, right? Then it's going to take those predictions and compare them to the real and try to calculate a loss. And then as we discussed this thoroughly, hopefully, last week, right, you should understand by now what Grad, backward, and step are doing because we discussed this last week, okay? So basically here you're doing, calculating the gradients, which basically tells you how to update the weights, add or subtract given the learning rate. All right, and then after that, we just print the losses. So let's go ahead and on that, okay? So we've got our training function. And now I'm going to proceed. Okay, so what do I do now? I'm going to instantiate my architecture, my CNN as model. I also initialize a torch optim. I'm going to use the atom optimizer. Notice that the parameters of the model are here, right? It get connected, and I specify the learning rate, which is something like 0.001 or something like that. Cross entropy, as I said, is the loss function. We've talked about FSC extensively, but we haven't really discussed this one. One of the things that I still need to do. All right, and then we run the model. Does this make sense, guys? Okay, so I'm going to go ahead and run it. We're almost there, I think. Hopefully there will be no errors. And it should start training. Did I do something?
Did you run the previous one?
I think so. I think I ran all of it. It's running, and this one has a number. This computer is very slow. Okay, so it should start doing this, printing. It might be that it's running and it just hasn't gotten to the epoch where it starts to print. It should print, no? Every iteration, right?
Yeah, that one should.
Mhm. Let me rerun this. All right, so I'm going to go over here. Kernel, clear outputs, restart. All right, let's go ahead and run this. All right, well, anyway, once it starts training, you should see the loss, right? And the loss seems to go down. You can see that these become like exponential, so they do become a little bit smaller. All right, and then we're just going to measure the performance of this, right? This is a classification problem, guys. So we should, guys. So we should see here on the diagonal, right? What does this tell you when you look at this diagonal of this confusion matrix, basically? Is it good performance or bad performance?
Pretty good.
It's pretty good, right? Exactly. So this is what you're looking for your model. Maybe it's time. All right, so it's going to be pretty slow, I guess. All right, so we have a few minutes left. So in this example, what I want to do is just play a little bit with the convolution construct itself, initialize a random tensor, and just see what happens. All right, so this is kind of a nice thing that I like doing all the time is just printing out the shapes, doing a little change here and there, and see what happens. So I'm gonna leave this for you guys to try. Okay, so at home, use the GPU maybe that I provided and see if you can get these performance metrics. And hopefully you'll have you'll see how it works because for some reason it's taking a long time. All right, so maybe going forward, I'm gonna have to start using the GPU in class. All right, so now let's take a look at what the convolution operation does to a tensor, basically. All right, so usually I call this something like figuring out the convolution maths for your model. All right. Guys, shh, keep it down, please. All right, so let's cell type, change markdown. All right. So basically, this is very simple and straightforward. I'm going to try to create a tensor run it through a convolutional layer and see what happens. Okay, that's essentially what this is. So this is probably in one of the 107 problems that I gave you. So here I'm going to create a batch. So n batches equal 1. Okay. So now I'm going to go here and create a tensor. All right, so my tensor, torch, just random values. Batches can be 1, 32, whatever I want it to be. And it's going to be n batch by 1 by 28 by 28, where this represents basically that's a black and white image. If it was a color image, I would change this number to what? 3, exactly 3. All right, and then I just print the shape of the tensor here. So I got my image, right? So a batch of one grid, 28 by 28. Now I'm going to instantiate a convolution. So you can see that here. So I'm going to invoke nn-conv2d. I'm going to specify that the input is 1, right? The grayscale, 16 filters of size 5 by 5 with a stride of 2. And I'm going to call it mathsconv1. Then I'm going to call mathsconv1, and I'm going to provide to it my tensor test, which is this one over here. So basically, the point of this is I'm going to run that tensor through the convolutional layer, and let's see what comes out of it. Obviously, what comes out of it is a tensor, but what matters is what the dimensions look like. Do you see that? And that's what I want to be able to figure out. So I can do that quite simply by printing out the shape. And so that's the advantage of it. So you can see here. And now I know that I gave it an image that was 1 by 1 by 28 by 28. And notice that what comes out, or sorry, a tensor. And now I got a tensor that's 1 by 16 by 12 by 12. Do you guys see that? That's the transformation that happened in this convolution. That's how I can figure out things. So for instance, remember how I just said in the architecture, I give it tensors, they run through the whole model. When I do the flatten operation, I know that this was 800. Do you see that? So one easy way of knowing that is just to print out the shape, right? So I do the flatten, I print out the shape after the flatten, and it's going to say 800, and then I can just plug this 800 there. Got it, guys? So this is how you can figure out and play with the tensors as you like. So that's basically it, all right? So we can take a look at more examples of this. So I have a tensor now, that tensor, right? So I call it resconv1, right? Resconv1. And it was 16. So now I'm going to go ahead and create a second layer. Right? My second layer is going to take in resconv1 as its input. Do you guys see that? And all I have to do is make sure I create another layer of convolution. This 16 matches this 16, right? And then I want 32 filters to come out. So then I'm going to call mathsconv2d. I give it resconv1, get resconv2, and print out the shapes. And I can see what the transformation did. Does that make sense? And that's really the key, honestly, to having command of these CNNs is just look at the shapes, and you can easily do it in this fashion. So you can see now 132 by 4 by 4, you can see that I wasn't lying, right? When I said that the max pool is somehow making them smaller. Do you see that? So from 28 to 28 to 12 by 12 to 4 by 4 and so on, right? That's just the nature of how CNNs work. Does this make sense, guys? Yeah, so this is how you can play with your architectures as you start to create things. All right, so we can keep going here. So if I want to maybe resize, I can use view, for instance, and PyTorch. So in this case, or flatten as was used before. So I just take resconv 2D, right? I use a view for it and I say, okay, keep the batches, but otherwise flatten it, please. All right. And so, now when I run the shape, it is 1, 512. So literally I have spaghettified the whole thing, right? So I took whatever, imagine a Rubik's cube or a grid, and I just made it into a specific vector. Does this make sense? Yeah. All right. So yeah, so this is kind of the example. This is probably this should be, these are just examples, actually. I have a couple of examples here, but I do have the problem, right? So since we only have about 7 minutes, I'll leave for you guys to just play with these examples. Use Conv3D and Maxpool with a large data set. Again, just create random tensors. In this case, you can create one that is 10 by 3 by 256 by 256. See what happens. Another example here, 10 by 1 by 28 by 28, right? And see what happens. This should be the actual problem, this problem. All right, so I'm going to basically see that this should give me the 800, right? And the 800 that I had here, right? So this 800 that I was able to figure out, I'm able to figure it out in this way. So I'm going to go ahead and assume batches of 10. Assume batches of 10, right? And then I'm going to create my architecture here. You notice this should be the same architecture, correct? And I'm using an n sequential, first convolution, 1 by 16, a max pool, then a second convolution, 16 by 32, a max pool, and then the nn flattened. That's the point where I spaghettify that tensor into the 800 in size vector, right? So that I create that architecture there. So I'm going to run that. Okay, that's done. Now I'm going to go ahead and what do I need here? So I'm going to create a batch. So the batch, let's see, I'm creating a random batch that is 10 by 1 by 28, which is like MNIST. That's called my tensor test. Then my tensor test goes into model RC. What is model RC? This one. You know that it's going to go through it, and the last thing that comes out is NN flatten. So then that's going to be in res actual model. So then I just print the shape, and there you go. So you can see it's 10 by 800. So that 800 is the value that I was able to figure out. And so when I want to add additional layers to my architecture, I just, I can. So from that 800, I add a new NN that converts to 512. And then finally, the final layer from 512 to 10. And that's so just playing with tensors to figure out the shapes, basically. All right. So does that make sense, guys? How you can figure out CNN shapes? All right. So anyway, so that kind of wraps up the lecture for today. So I gave a very quick and dirty introduction to CNNs. Please read the material, discuss the intuition. We did one simple CNN example, right, for MNIST, and you also saw how to play with the tensor shapes. Okay. All right, so it's 6:16, so let's take a 10-minute break. So I'll end the class right here. Do you guys have any questions before I proceed to the exam? All right, so I'm going to stop the session here. All right. Okay, so we'll start the exam in 10 minutes exactly. So at 6:16, let's take a 10-minute break, and at 6:27, we can begin the exam. Okay. All right. So thank you.